In this video, we'll introduce the idea of multitask learning. So in the previous video, we discussed a convolutional architecture for a neural network that would give us a model for the unary potential in a linear chain conditional random field for solving any individual word tagging problem. And then at the end, I mentioned that so we could use such a neural network individually in a single specific neural network for each task and solve them individually. However, this might seem suboptimal in the sense that these tasks they appear a little bit related. So for instance, pause tagging, which helps us identify nouns and verbs in a sentence, is probably related to the problem of identifying noun phrases and verb phrases. Also, identifying verb and noun phrases might be useful for identifying what are the segments which correspond to a single role with respect to a verb. So there are probably relationships between chunking, between identifying noun and verb phrases, and identifying the semantic roles of words with respect to different verbs in the sentence, so semantic role labeling. And so one way of tackling this problem would be to essentially develop a single conditional random field to model the joint distribution of all the labels for all the different tasks. However, if we do this by, say, introducing connections or pairwise potentials between the labels of different tasks, then we'll eventually face a problem where performing inference at test time and during training will not be possible to do exactly. We have to do approximate inference, which is a little bit inconvenient. And so here we'll look at a different approach that Colabert and Winston decided to use in order to still allow some sharing between the different tasks while not having to design a conditional random field that would be too complex to allow for efficient and non-approximate inference. The approach is actually very, very simple. So we'll use individual neural networks for each of the different tasks, except for the lookup tables. That is, except for the matrices that contain the word and feature representations for all the words in our vocabulary. So the idea is that each task will go and update the parameters of the lookup tables, and the only parameters of the unary potentials are going to be specific for a given task is the rest of the neural network. So the convolution, the linear transformation into the hard tangent, and so on. Everything else is actually going to be so all of these parameters are going to be specific to different tasks. The only thing is that they all share the same word representations. And so we'll be able essentially to have a better representation for a word by combining information about what its pause tag is, what is its role in participating into noun phrases, or the semantic roles with respect to verbs, or whether it's a named entity or not, and so on. And so this will help make the word representations across the different tasks richer, but we'll still have specific parameters for solving each of these tasks individually. So this is a form of multitask learning. In general, we refer to multitask learning as a type of learning where we try to solve multiple tasks simultaneously. And it's a very simple one where we just share parameters across different models which otherwise would be treated separately. And so it's a very simple, straightforward way of at least allowing for some sharing of information between data sets of different problems. And another thing we could do is actually invent certain tasks to try to make even more richer the word representations that we learn. So one task that they thought about is a task inspired by language modeling. So what you would do is that, so the task that they thought about was that it would take a window of text, say 5 words, and then the task would be to determine, if I give you a particular window of words, whether the word that is placed in the middle is actually the original word that was taken, that was observed in the original text. So one way of generating a data set for that is to take all the word windows, say, of 5 words, and so we pick these different windows of words from some unlabeled corpus like Wikipedia, and then we generate a bunch of negative or imposter words context by just replacing the middle word with a different randomly chosen word. So the actual original windows would correspond to the positive example of that problem, and then the negative example would be these other word windows where we've taken the middle word and replaced it by some randomly chosen word. Now you might think that you might actually pick randomly a word that would still make sense as if we actually observed it in that context. So for instance, if we were replacing the, and instead of the we picked a randomly, so it would be cat sat on a mat, that would still make sense. So it's perhaps a little bit strange to treat that as a negative example, something that we don't want the neural network to think is likely, but still, this is only trying to influence the word representations, and because there are many more words that are going to be wrong than there are words that are going to be good words, this is still a good way which works well in practice for generating data for this task. In particular, this extra task, which is going to be solved using the same word representations as in the neural net that tries to do word tagging, the way they're going to tackle it is using a neural network which takes just this context of 5 words. So it's, in this case, this neural network is not going to be a convolutional neural net. It's going to be a regular neural net, but that uses word representations and tries also to influence them through gradient descent. And the loss function that they decided to use, so we could design some sort of binary classification problem using softmax output with 2 possibilities, for instance, that could have worked, but instead they use a margin inspired, a loss function that's inspired by the idea of maximum margin between different classes. And specifically, what they're trying to do is that if we know f theta x as the output of the neural net, which outputs a score as to how good the particular configuration of the word window in its input is, how meaningful it is based on according to the neural net. So if we have f theta of x for the original window, and then for a window of text where we've replaced the middle word in the window by some random word w, so f theta of xw, if we know that as the score for this imposter window, then it would try to minimize this expression here. That is the maximum between 0 and 1 minus this score plus that score. So another way of writing this is we'll put parenthesis here and then replace then that by a minus, because it would be cancelled out by this minus. That's why it's a plus in the original expression. So effectively what we're doing is that we're looking at the difference between the score as assigned by the neural net, which has just a single output, and it provides us with the score for the input, the context window we're providing it. So we look at that score and we subtract it by the score for an imposter window. And now, if that difference is larger than 1, then we have 1 minus a number that's larger than 1, which is negative. So the maximum between 0 and that is going to be 0. And so in this case, the loss is exactly 0. We're not incurring any loss from that prediction. However, if the score for the the original window and subtracted by the score of the imposter window is smaller than 1, so if the margin between the score of the true window and the score of the imposter window is not bigger than 1, in this case, then we're going to have 1 minus a number which is smaller than 1, so we'll actually be incurring a loss which is non-zero. So what the neural network is trying to do is to push the score of the original window to be at least 1 more than the score of any other imposter window. Okay, so that's intuitively it's essentially trying to separate imposter windows from true windows. And like I said, it's trying to enforce a margin between the true windows, the original windows, and the imposter windows. So this is similar also to language modeling in spirit, in the sense that instead of predicting the next word, we're predicting what is the word in the middle, and we're trying to make sure that we assign a higher score to the true true windows that contain the right word instead of an imposter word. And so for that reason, in the original paper, sometimes they talk about this task as a language modeling task, even though it's not a language model based on the definition of a language model as being a probabilistic model that assigns a probability to any sequence of text. But just so you know, if you look at the paper, that's why they call it a language modeling task. It's because it's similar in spirit with language modeling in general. So let's look at some results taken from the journal version of that paper by Colobert and Weston. So we have here the results for the pause tagging, chunking, name entity recognition, and semantic role labeling tasks for some benchmark systems that are taken from the literature, so they're usually not neural networks. And then the neural net that uses the convolutional approach, and a different convolutional neural net for each different tasks that is used as the unary potential for a conditional random field. And also in this particular neural net, no features are used. The only feature that's used is the original word, but we're not extracting suffixes and prefixes. So we're trying to see whether the neural net can learn a representation from scratch without any information as to what are useful features to extract from the original word to get a good performance, which is something that these benchmark systems do. And we see the performance is not too bad, but it's usually below the performance of the benchmark systems. However, if now we either use the language model as an extra task that is used to influence the word representations that we're learning, and also if we add up on top of that the possibility of having all tasks influence the word representation, so if you do multitask learning, then we see that we get a very big improvement with respect to the original result we got with the neural net. And we're actually quite close to the baseline system. So here we're almost exactly at the baseline system. Here we're a bit more below, but not that much worse. Again, here 88 instead of 89. So we got a big jump from 81 that we had initially. And here 74. Which is lower than 77, but much better than the 70, almost 71 that we had before. So what's interesting here is that just based on the training data, and without any information about what are the good features to extract, so whether we should use suffixes and prefixes, it actually was able to do a really good job and almost match the benchmark systems, which have a lot of hand tuning in terms of what are the features that were extracted, so which required a lot of work from the human experts behind the model that designed it. And then they tried to see, okay, well, what if for these different tasks we actually introduce these other features that are known to help for trying to solve these other problems. So suffixes are known to help for pause tagging, and indeed then we match the performance of the best pause tagger. Gazetteer features are helpful, and indeed then we match the performance for name entity recognition. Pause tags, if we add as the input the pause tags of the words, this is useful for chunking, and indeed we match the performance of the best system, which usually do this kind of pause tagging extraction. And for semantic role labeling, we get a little bit of a boost compared to the original performance, but we don't match yet the benchmark systems. But for these three other tasks, we actually did sometimes a little bit better. So we see this is a very competitive approach for word tagging, for a bunch of different word tagging problems, and this is all based on a neural network that learns word representations. And a fun thing to do then is also to try to visualize the quality of the word representation. And one way of doing this is to take different words, say France, which has word ID 454. That's not really meaningless. It could have been anything else, really. And then look at what are the nearest neighbors in word representation space if we consider all other words. So we go over all the words in our vocabulary, look at their word representation, compare the distance, the Euclidean distance, with the word representation of, say, France, and then we report the nearest neighbors. And for instance, we see here that, say, for France, we get a lot of other different countries in Europe. So for Jesus, we got a lot of religion-related words. Xbox, we got some technology and often gaming console words. And reddish, we got greenish, bluish, pinkish, megabits, other computer science related terms. So we see that it seems to have, in some fairly real way, understood what these words are. And you can also try to get a 2D visualization of these word representations. And you can look on that URL here to get a 2D mapping of the words, and you see it's quite impressive, the understanding of these words that was learned by this model. And so that's it for how to solve word tagging problems with neural networks.